Hello all, and welcome as we continue to explore circular functions. Today we're going to look at sine and cos graphs, or sine and cosine graphs. Here's a screenshot taken from the Maths is Fun website. There's a link there if you want to use it to go to it. So we're going to jump in and look straight away at if we graph sine of an angle and cos of an angle and even tan of an angle, but we'll just focus on the sine and cos at the moment as we change angle. Now the thing to note is our x-axis is now our angle, and then our y-axis is either going to, it's effectively the size, okay, of sine or cos, okay? Or we could also think of it as the magnitude of that. So let's jump over to Maths is Fun and have a look at how this works, okay? So the way this is set up at the moment, I've got mine selected where I've selected coords, degrees and circle to show. As I move my mouse around, it draws a radius of unit 1 along my mouse, and it also shows you on the left-hand side in green how big the vertical component is, and in blue how big the horizontal component is. And then on the right hand side it shows you a graph starting at an angle of 0 going on, and it's tracked all the way around up to 360 degrees. Let's start by looking at the green graph on the right hand side. The green graph represents sine, so sine is our vertical component. So let's have a look at my radius is drawn at angle 0 degrees, as it is now, so right there along the x-axis. How big is the vertical component of it? It's 0, so the graph starts at 0. So looking at the right-hand side, the green line starts at 0 at the origin. As I increase my angle, you can see the vertical component gets higher and higher and higher, and as we track along on the right-hand side as well, you can see it gets higher and higher and higher until we get to the point where the angle is 90 degrees and the vertical component is perfectly 1. So we get there. Then as we go past 90 degrees, my vertical component gets smaller and smaller and smaller and gets back to 0 at 180 degrees. As I keep going past that, my vertical component gets bigger and bigger and bigger, but it's now in the negative direction. So we can see on the graph on the right hand side, it's down negative at like negative 0.777 at the moment, and keeps getting larger and larger and larger until it gets to negative 1, which occurs at 270 degrees, and then it gets smaller and smaller and smaller again, and it gets back to 0. Now, if I kept this going on, and I've done one full rotation, I kept going on towards, say, 540 degrees, 720, this process, this wavy line will repeat. The exact same thing can be done for cos. Let's instead look at the horizontal component, start at 0 degrees. My radius is drawn in, the horizontal component of 1, but as I increase the angle, the horizontal component gets smaller and smaller and smaller. It's currently at 0.755. It gets smaller, 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 smaller. It gets to 0. And then as I increase the angle, it now increases again, but in a negative direction. So we can see negative 0.669. Keep going to get to negative 1 and goes around. So you can have a play with this to start looking at that relationship. And you've done circular graphing sine and cos last year, so hopefully this is pretty familiar. There's a couple key bits to take out of any sine and cos graph. Okay, one is the time it takes to take one complete cycle, okay, which is the same as doing one full revolution of the unit circle. And that happens to be 360 degrees, or it also happens to be 2 pi for a standard unit circle or a basic sine theta. The other thing to note is the amplitude, which is how high it gets and how low it gets. In this case, it's 1 and negative 1. Again, for a standard unit circle or a standard sine function. So they're the key things to take into account, is how long it takes to do one whole loop, and we call that a period. And then how high and low the graph gets at its highest and lowest points, and we call that amplitude. And we will talk about those lots. Cos has the exact same thing. It just so happens that it starts at 1, goes down to 90, gets to 180, back up to 270, and then 1 period has occurred. Has the same amplitude, has the same period of taking 360 degrees or 2 pi to go through 1 full cycle. It's just that the cycle looks a little bit different. It starts at 1, ends at 1. So, as I said there, period is the set of x values that a trigonometric function takes before it repeats itself. Amplitude is the distance from the middle up to its highest point or down to its lowest point. And we can write those in, okay, or if we have a function where we put an a at the front and another coefficient inside the sign, this a is going to impact the amplitude. Okay. And a is effectively directly represents amplitude, but n, I'll say, impacts period. It doesn't tell us exactly what the period is. We have to sub it into this thing down here, where period will be equal to 2 pi divided by n. So whatever this is in here, do 2 pi divided by that, and that will actually tell us the period. And that holds, and hopefully this is a refresher from last year. So, for example, we have a graph of 3 sine 2 theta. Okay. Well, the period is going to be equal to 2 pi divided by n. N is this number here, 2, so we get 2 pi divided by 2, so our period is now pi. So if I was to graph that, and a sine, we know starts at 0, ends at 0 for its... my PowerPoint is just frozen. If we give it a sec. Okay, there we go. So we're doing theta this way and size of sine this way. Starts at 0, ends at 0. We're going to have some repetition like that. How long is this repetition? Well, we got our period, so that point there needs to be pi. Our amplitude we can read straight off the front. That's our A. Okay, so amplitude is equal to A, and in our case, A was equal to 3. So the highest peak is at 3, the lowest peak is at -3. So we're just going to go through and check a bunch of these. So amplitude, number straight off the front, for this one is half. Period is going to be equal to 2 pi on n, which is equal to 2 pi on 2, so equal to pi. Amplitude, it has a negative here. Since there's no number, it's effectively saying -1. Now, amplitude, we don't give a sign. It's just a size. So the size of the amplitude is still 1. It's not negative or positive. We just say it goes up to 1. The period is 2 pi on n, which happens to be 2 pi. Now, n in this case happens to be 2 over 3. So we've got 2 divided by 3. Now, how do we do 2 pi divided by 2 on 3? Well, that's the same as 2 pi times by 3 on 2. So that gets us 2 and the 2 cancel, leaves us with 3 pi. So that's my period. Amplitude for C, again we ignore the sign, so the amplitude is just half. The period is equal to 2 pi divided by 3 pi on 4. That's my n there. So how do I do that? 2 pi times by 4 on 3 pi. So that's going to, the pi's in this case cancel. 2 times 4 is 8, so I get 8 on 3. So that's my period. So that's finding those. We can also, if we find those, once we find those, it's really easy to graph. We're going to get into, at the moment, we're just concerned about doing, I guess, a rough sketch, and we're not so concerned about all the intercepts. We almost get the first, especially for sine, we get the first and third intercept. The second one will always just be half of the period. So you can find it that way. We will look at in the next exercise in 6E how to actually solve the equation when we let it equal to 0. But at the moment, just go with, we're trying to find how long is one cycle and how high and low does it get. We can also use our CAS to do this. The instructions in the textbook show this, that you could, if we go into menu, and we can go graph and table, and you could type in your function there. For example, we can go, where's keyboard? we want cos of x, and then we want to use this vertical up and down line, and that's what this is talking about down here, that it means such that or given, and that allows us to put our domain in. That's found in the Math 3 over on the right hand side, straight up and down the line, and then we can put in our range. So we want from negative pi is on all pages, that's handy, negative pi less than or equal to x less than or equal to 3 pi. Click on it, put a tick in the box, hit the graph, and my window is very zoomed out at the moment. Something else, so I'm just going to... Oh, I'm in degrees, which is no good. I need to change to radians, and that's why that wasn't working. The other way we can change our window is you can go into the window button, which is here with the arrows inside it, up the top in the middle. Click on that, and you can put in numbers, and you can even put them in either decimal or radian form. That'll work fine. But you can certainly use the zoom box just to draw a box around your graph, and it'll zoom into that. And there we can go. And we can see, like we had, amplitude was 1, n is technically 1 as well. So for our graph, amplitude should be equal 1, and our period should be equal to 2 pi divided by 1, which is just equal to 2 pi, and we can see that. Scale here, this is a really handy thing. You can set the scale in radians as well, so we might just call it pi on 2, and it's actually put marks now at pi on 2. It still labels them as decimals. You can see that's 7.85. That's the equivalent of what's that, 3 pi? Wait, is it 3 pi? No, that's 1 cycle to there. That's 2 pi. Yeah, 3 pi. But yeah, that's a really handy trick, is to set your scale to, and it's changed it back to a decimal, but we could have just set the scale to pi. Okay, and it's put a line every single pi. So that's pretty handy. So that's how you can graph it. Just make sure you're in radian mode. You'll really struggle. Right, so using your sketch a graph of y equals cos x for 2 complete cycles on the axis below. Also state the domain, range, amplitude, and period of the function. Well, straight away we can get a is equal to 1, period is equal to 2 pi on n, which is equal to 2 pi on 1, which is equal to 2 pi. And if we remember, our cos graph starts at 1, it's going to end at 1. That means halfway between, it needs to be down at -1. So there's going to be our intercepts there. Down, over, up. So I'm doing this even without the cas. Well, let's go into the cas. The other thing is we've typed it in y equals cos x straight away here. Remember, a big thing that we should be doing, especially if we're in the exam, we're using a function several times or it has several parts, really, we should be defining our function. So if we go define, let's just call it f of x is equal to cos of x, and we can put our domain in that definition, which is actually a really smart thing to do with circular functions. If we're defining it, try and put in a domain. Even if you're not sure, it's not given the question, put something in that would make some sort of sense. So we want between 0, and we're doing 2 complete cycles. We found periods 2 pi, so 2 cycles will be 4 pi. So we're going less than x, and x is up to 4 pi. And execute that. So we've defined it. Now if we go back into graphing, instead of that, we can just go f of x, click graph, and zoom. Let's zoom out just a little bit. There's a graph. 2 complete cycles, so we're just sort of copying that. It's going to go pi. Yeah. Okay, so there's that. Starts at 0,1, ends at 4 pi, comma 1. Says state the domain, range, amplitude, and period of the function. So we've done amplitude and period. We just need domain and range. It's obvious to see the domain is x is from 0 to 4 pi inclusive, and our range, our y value, is between -1 and 1. So there's a quick graph. Use your CAS to sketch a graph of y equals negative cos x for 2 complete cycles on the axis below. You must also state the domain, range, amplitude, and period of the function. Let's go a negative sign instead, just because we've already done cos on the next one. We'll do sine. So amplitude is equal to 1. Period is equal to 2 pi on n, which is equal to 2 pi on 1, which is equal to 2 pi. So that means 2 complete cycles is going to go to 4 pi. So it's going to start at 0. It's going to go to 4 pi. Now sine, before it's translated, it starts at 0 and ends at 0. So let's go back to main. Let's rechange this to sine. And we're going to redefine it. Go back to the graph. Sketch it again. So we can see there we can steal off our CAS. But we know one cycle, the period is equal to 2 pi. So it needs to go all the way up, come down in the middle, go all the way down, and go up. I made a mistake there. I need to make this negative. Okay. So what will negative do? Negative will reflect it. So a regular sine graph will go up, but in our case, it's going to make it go down instead first. Come up, go up. And there's one cycle. Starts at 0, ends at 0. And then it's just going to go through the cycle again. Domain is just like on the previous slide. We have 0 to 4 pi, and range is exactly the same. The lowest value is -1, and y goes up to the largest value of +1. Ooh, go in my CAS, double check that, and let's just double check, make sure CAS gives me the same thing. It does. There we go. Goes down, up, and around, full 2 cycles. So that matches. One more quick example. We've got sketch graph of y equals 2 sine pi on x equals 6, 4, x between 0 and 12 on the axis below. Also state the amplitude, period, domain, range. Okay. Amplitude is equal to 2, period is equal to 2 pi divided by pi on 6, which is equal to pi times by 6 on pi. Pi's cancel. So that's going to be equal to 12. That's handy. So equal to 12. It's a sine graph, so it's going to start at 0, end at 0, goes to 12. Where's 12? There. The midpoint is going to be halfway between that, so that's 12. This will be at 6, 0. That's 12, 0. That is 0, 0. So we have that. The amplitude is 1, so the highest point it's going to get up to will be 1. The lowest point it's going to get to is -1. So we get to that. And we're doing this tech free. Now, how do I know how far left and right those are to do? Is that if we just look at this, we can sort of split the graph into 2 halves. We have our first half and we have our second half. And then within that, we can split that into quarters. So we have the quarter point, we have the halfway point, we have the 3/4 point, and then we have the full period. So whatever the period is, we can split it into 4 parts. So our period was 12, so the first quarter point is going to be at 3. The halfway point is going to be at 6. the 3/4 point is going to be at 9, and then the finish of the period is going to be at 12. So that's how I've put my 0, I've put the halfway point in, and I've put the 12 and the full point in. Now I'm going to the quarter and the 3/4 points, which are at the peak, the top peak and the bottom peak. So that's going to be at 3, and the other one's going to be at 9. So that's how I know how far left and right to put them, is because of this symmetrical nature about the graph. So just need to connect the dots, state the period, domain, and range. So domain is from 0 to 12 because we're doing it for one cycle, and we're actually also told that's our domain. The range is just the amplitudes. So range is from -1 to 1. So there's our graph. From this, if we wanted to think about what are we up to, we're up to 21 minutes already, so I'll try and make this quick. I'll leave the exam practice questions to do at the start of class. They can be a good warm-up. Is what are these numbers actually doing? Well, one number's changing the period, so that we can think about it may make, let's try that again. Like that's one cycle, but if as we change the period, it might stretch it out, or it might make it really short. Okay? So that's the effective period, which happens to be stretching it out left to right, or we are dilating from the y-axis. That's the effect of period. And then amplitude, well, we might have the regular one. It might get really big, or it might get really small, but we're effectively stretching it up and down, so we are dilating from the x-axis. We're stretching it up and down. So we can still apply all our transformation rules, or we can read off the dilation transformations pretty much easy, or we can apply them to the graph really quickly using our exact same rules. If we're told to dilate from the x-axis, so we're impacting our y values, we just replace y with y on b like normal. If we're dilating away from the y-axis, so in this case we're stretching left and right, we're actually affecting the x-coordinates. That previous one was stretching up and down. We just replace x with x on b, our same replacement rules. So, given the function f of x is equal to 5 cos x, give a sequence of transformations which takes the graph y equals cos of x to the graph of 5x. So we follow all our same rules. We want to write it as, so we have y equals 5. We're starting with, sorry, let me restart that. Y is equal to cos x, and we want to go to y is equal to 5 cos x. Now we want to write it where our coefficients are applied either directly to the y or directly to the x. That 5 is not, it's outside the cos. So we would rewrite that as y on 5 equal to cos x. We can quite clearly see we just need to replace y with y on 5, which as it says here. So if we're replacing y with y on 5, we're affecting the y coordinates. That means we must be dilating away from the x-axis. So we can see it is a dilation of factor 5 from the x-axis. I'm just trying to go through this quickly. You can take a little bit more time to read through that. But let's have a look at, for each of the following, give a sequence of transformation which takes the graph of, and we're starting with f of x is equal to sine g of x to the graph of y equals g of x, where we have two options down here. So the first thing we need to do is rewrite these in terms of something affecting directly to the x and directly to the y. So this one we'd actually change to 2y is equal to sine x on 3. And we're starting at y equals sine x. So what are the replacements? I might actually write this down at the bottom. 2y is equal to sine x on 3. And I'm starting at y is equal to sine x as per the question. What are replacements? Well, it's clear I need to replace x with x on 3. Gives me y equals sine x on 3. Now the second one, how do we get the 2? Well, we can replace y with 2y, but we want to think in terms of y on something. Well, that would be the same as replacing y with y divided by half, because y divided by half is the same as y times by 2 on 1. So we've been dividing by a fraction, now we multiply by its reciprocal, which gives me 2y. And that gives me my final thing. So I can just read off here, if I've replaced x with x on 3, that is dilate by 3 from y-axis, and here I've dilated by half from x-axis. And the same over on this last one. So y is equal to 3 sine 2x. So we want to write this as y on 3 is equal to sine 2x. This 2x again we want to try and rewrite as x on something. So this is the same as y on 3 is equal to sine x on half. So we can clearly see to go from sine x to this one, we've had to replace y with y on 3. So that's dilate by 3 from x-axis. We've also had to replace x with x on half. So we've dilate by half from y-axis. So that's how we can graph. Sorry, let me not jump too far. That's how we can find or apply basic transformations. And prior to that, our goal was just looking at sketching basic graphs of sine and cos. And by finding the amplitude and the period, we've effectively found the horizontal and vertical dilations. We just aren't applying any translations yet. As soon as we start to apply translations left and right and up and down, this becomes a whole lot more complex, and especially trying to find the intercepts becomes a whole lot more work. But that's our start of graphing sine and cos. To view these two questions, question and this one, you'll need to download the PowerPoint and put in play mode and then click through to get that to appear. But yeah, have a go at those at the start of class. If you have any questions, feel free to email, ask in class, put in comments below or in Google Classroom. That's it, and have a good day.